are acids. What's kind of our clue that we're looking at acids? What's a signature characteristic of acids? Hydrogen, okay, and specifically, you typically know that it's an acid because the hydrogen is written first in the formula. So you see we've got some generic acids, HX, HY, and HZ. So when you put an acid into solution, what happens to that hydrogen? Yeah, so we think about ionization, or that's probably the word you guys are using, ionization. So essentially what that means is that if I've got an acid, and I'm going to go for another generic acid, HA. So HA can be aqueous, it can be dissolved in solution. When it breaks apart, we can get H plus ions, and we can get A minus ions. Okay? That's one way an acid can behave in solution. There's another way an acid can behave in solution, which is very similar. Okay, and the only difference there is the arrow, and that was kind of a sloppy arrow. But essentially, the difference there is one has this all the way in the forward direction arrow, and one has this back and forth arrow. So you guys remember talking about those different kinds of arrows? Not at all. All right, so the first one is a strong acid. The strong acid dissociates completely, breaks apart completely, ionizes completely, whatever word you're using to talk about acids. So that means that everything that was HA is now H plus and A minus, so 100% dissociation or 100% ionization. The one with the back and forth arrows is what we call a weak acid. So being a weak acid, it does not ionize or dissociate completely. It only dissociates maybe 1%, not that much. So essentially what that tells us is that for a weaker acid, we're actually going to have mostly this HA. We're going to have very little H plus, very little A minus. So that's the difference between a strong acid and a weak acid. All right, so what does this have to do with electrolytes? Does anyone remember a definition or just a general description of what an electrolyte is, or what it does, or how it behaves? Just a word we like to use because chemists make things up all the time. What's an electrolyte?
It ionizes.
Okay, so an electrolyte is something that ionizes in water. So the electro part of it has to do with conducting electricity or movement of electrons, having ions, okay? So if you had to pick out which of those is going to be a better electrolyte, which one's going to be better at ionizing, the strong acid or the weak acid? Strong acid, because it's ionizing completely. So a strong acid is a strong electrolyte. This is how it's tying together. So strong acids are strong electrolytes, weak acids are going to be weak electrolytes. Not a trick question here, all right? So how does that help us understand what they look like? Well, the H₃O plus is really just a combination of H plus and H₂O. Okay, so we call that the hydronium ion. So sometimes you'll see us just write H plus, sometimes we'll write H₃O plus. It means the exact same thing. So if I'm trying to figure out which of those is the strongest acid, I'm trying to figure out which one of those is going to make the most H plus ions, and I can identify that it's making the most H plus ions because it then creates the most H₃O plus ions. So the one with the most H₃O plus is HY, and we can tell that because it's got the most of those red ions in there, so that has to be our strongest acid. So how would you classify HX and HZ? What kind of acids would those be? Those look like weak acids, right? They're not producing a lot of H plus, we're not getting a lot of that H₃O plus. Any questions on the relationship between strong electrolytes and strong acids? Questions about what the arrows mean? Yeah. Okay, so the ones you're used to seeing are these, just the normal straightforward arrow, and that means that this thing completely goes in that direction. So it's the normal reaction we write means 100% breaking apart. This arrow is going to have like a forward one and a back one at the same time. We sometimes call it an equilibrium arrow. Essentially, it tells us that this reaction does not go 100% in the forward direction. Some of it turns into this, but sometimes this can recombine and go back this way. Essentially, what it tells us is that we do not have 100% ionization, only a little bit of ionization. That's the difference between your strong electrolytes and your weak electrolytes. So the only way you're really going to see weak electrolytes are weak acids and weak bases. which means you need to be able to identify them so that when we talk about what kind of electrolytes we have, you know which ones are weak and which ones are strong. Have you talked about which acids are your strong acids yet? A little bit? Okay. So there are 6 strong acids typically. Does that sound right? Do you guys have to remember 6 of them? All right. And the way I remember them, and this doesn't work at all, but is CSI and BC. I'm aware that CSI airs on CBS, but it doesn't work for my mnemonic, so we're going with this one. So the 6 strong acids, obviously I can't just tell you what letter they start with, because all acids start with H, and if you remember HHH, that's not going to be terribly helpful. So the letters are the second part of the acid name. So the first C, that can stand for hydrochloric acid, HCl. The S, that can stand for sulfuric acid, H₂SO4. The I can stand for hydroiodic acid, HI. Any guesses on what the N stands for? Yeah, nitric acid. You got it. Not so bad. HNO3. The B, hydrobromic acid, HBr. And then the last C is perchloric acid, and that's HClO4. So those are your 6 strong acids. Any other acid you run into is going to be a weak acid unless it's some kind of strange super acid that you probably won't have to worry about. But those are the 6 strong acids you'll typically have to worry about. And again, that's one way I remember them. There are plenty of other ways. But it's easier just to have those memorized for right now. That way you know when you see strong acid, you know it's going to be a strong electrolyte. And again, that means when we put it into solution, it completely ionizes. We would use this kind of arrow, the forward arrow, to indicate what's going on with that acid. So we've got aqueous solutions of cations, which are represented in red, and anions, which are represented in yellow. They're allowed to mix, and I want to know which one of these pictures, 1, 2, and 3, is going to give me the best representation if I assume that this reaction is the mixture of sodium ions and carbonate ions. So if you have solubility rules or your book on you, you might want those. If you don't know your solubility rules, you might want to think about 2 possible options. If it is soluble, it would look like this. If it's not soluble, it would look like that. But go ahead and talk to your neighbor again. Think about this one. I will walk around, so stop me if you have questions. All right, so our product should be sodium carbonate, and what's the formula for that going to be? Good. All right, so the question is, do we put that with an S afterward? Is it a precipitate, or do we put an AQ at the end? So shout it out, what do we think? It is aqueous, okay? So we know that it's going to be aqueous, so now the question is, which one of those pictures best shows an aqueous solution? So again, hands up for 1. Okay, hands up for 2. Hands up for 3. All right, so I think the best choice here is choice 1. And the reason I like choice 1 the best is, to me, something that's aqueous means that it's still dissolved in solution, right? So it should have ions that are free to move around and kind of mix with water. So that's what I would expect to see for an aqueous solution. 3 is what I would expect to see if my precipitate was there, so if it was a solid, essentially. Because we know that precipitates, since they're solids, they tend to settle out and sink to the bottom. And to me, what this picture is trying to represent is that all of my ions have kind of condensed and they're now in this solid state. So we don't want to think about there being water in between them anymore. We have these solid ionic structures now. 2 would be the case if we had a limiting reactant. Okay, so if you look at the ratio here, you see how there's 1 red for every 1 yellow in number 2? Well, if you look back at the formula for sodium carbonate, it's Na2CO3, which tells us we actually have a 2-to-1 ratio of cations to anions. So this would only be the case if we had a 1-to-1 ratio of cations and anions, and we had some extra cations floating around in solution. So that's not the case because we don't have a limiting reactant. All right, before we go through these, let's just talk real quick about the definitions of each of these types of electrolytes, and that should help us answer this question fairly quickly. So how does a non-electrolyte behave? What is a non-electrolyte going to do when you put it in water? Nothing really. It might dissolve, okay? So like sugar is a non-electrolyte, and sugar dissolves. So we're not saying it doesn't dissolve, but there's a difference between dissolving and dissociating or ionizing, okay? So when you put a non-electrolyte into water, you get no ions. Okay, so what about when you put a weak electrolyte into water? What would you expect? Yeah, that's basically it. Which must mean that when you put a strong electrolyte into water, it does what? All of it turns into ions, so we call it a complete ionization or complete dissociation. Okay, so we know that, that's fine, but just because we have the formula for something doesn't necessarily tell us what it's going to do when you put it in water. So the next thing we want to think about is what are some typical examples or what classes of substances fit into these different categories. So I already gave you an example that sugar is a non-electrolyte. What kind of general class of compounds do you think you might be able to describe as non-electrolytes? Yeah, molecular compounds are typically non-electrolytes. The only thing we need to say here is except acids or bases, okay? Because acids and bases are going to be either strong electrolytes or weak electrolytes, depending on if they're strong acids, strong bases, weak bases. So typically covalent or molecular compounds are non-electrolytes unless they're acids or bases, which is why it's important for us to be able to recognize acids and bases. Weak electrolytes, the only time you're really going to see weak electrolytes is if you have a weak acid or a weak base. Strong electrolyte, strong acid, or strong base. There's one more class of compounds that's going to be a strong electrolyte. So not thinking about acids or bases anymore, there's another kind of general class of compounds that would be considered a strong electrolyte. Anybody know? Something that's not an acid or base, but when you put it in water, it's going to completely break apart into the ions it's made up of. Soluble ionic compounds, so salts. And actually, not all salts are soluble, but soluble ionic compounds. Which means technically up here for non-electrolytes, your insoluble ionic compounds also go up here. Okay. So that solubility chart I just showed you guys, that really only helps with this piece of the puzzle right here, right? All that does is tell us if we've got a soluble or an insoluble ionic compound. The acid or base thing, that's going to be up to you to remember. So let's go ahead and go through these. So what do you notice about substance A, H₂SO3? Can you tell anything about it? Sure you can. It's an acid. Now how can you tell it's an acid? It starts with a hydrogen, okay. Is it a strong acid? No. How can you tell? Not on the list I just gave you. Okay, so if it's not a strong acid, it must be a weak acid, which means it must be a weak electrolyte. Questions about how I made that leap? All right, C₂H₄OH, better known as ethanol. What do we think? It's a non-electrolyte, and why would it be a non-electrolyte? Yeah. So ethanol is a molecular compound. Notice that it has hydrogens in it. So not everything that has hydrogen is an acid. What's the takeaway? How do you tell if something that has hydrogens in it is an acid? How do we kind of hint that to you that it's an acid? We tend to put the hydrogens in front. Not always, I'm not going to promise you we always do that, but most of the time if it's an acid, we'll put the hydrogens in front to kind of tip you off that it's an acid. So even though this has hydrogens in it, it's not an acid, it's actually an alcohol, ethanol, and that's a molecular compound, so it's a non-electrolyte. All right, what about C, NH3? Anybody recognize that? Do you know the name for it? It's ammonia, okay. Any acid or base properties there? And it's got hydrogens. This is another time we're being a little tricky. Ammonia is a weak base. You just need to know that. Ammonia is a weak base. So if ammonia is a weak base, what kind of electrolyte is it likely to be? Weak. Yep. Any questions about that one? Yes.
Is there any way, like, you know, like, if you can tell if it's an acid, if there's a base, is there any way to tell out the bases?
The only bases that are easy to identify are strong bases, because those are your metal hydroxides. So potassium hydroxide, sodium hydroxide, magnesium hydroxide is strong base, but it's not always soluble. So strong bases are easy to identify. Weak bases are not. Ammonia is going to be the number one. Basically, all of the other weak bases are related to ammonia. So if you see nitrogens and hydrogens, that's a pretty good guess that it's going to be a weak base. But there's something you just have to get familiar with by seeing a lot of them. And that's what makes this problem really hard, right? You have that whole solubility table, and very few things in this problem are useful with the solubility table. So there's a lot you need to know on your own about acids and bases to do this. All right, D. How do we classify that? Just in general, does it look familiar? Do you have any idea what it might be? Are we thinking acid or base? Not really. So it's probably just a what? Is it molecular or ionic? It's probably ionic, and how can you tell that? It's got a metal and potassium. Now, I don't remember ClO3 minus being on your solubility rule, so we're going to kind of have to make a guess here. But what do we know about compounds that contain alkali metals, things from the first column? They're normally what? Soluble. Okay, it's a pretty good bet that if it's got an alkali metal in it, it's going to be soluble. So if I've got a soluble ionic compound, what kind of electrolyte am I looking at? Yep. Any questions about that one? All right, and then what about the last one? Knowing everything that you know now, which one is it most similar to? Which one does it seem to have the most in common with? In terms of being a class of compound you recognize. Well, what's copper? It's a metal, so we know that it's likely going to be an ionic compound. All right. If you think back to your solubility chart, nitrates are another one that pretty much 100% of the time nitrates are soluble. So again, I have a soluble ionic compound. Soluble ionic compound means what kind of electrolyte? Strong. Let's only do B. Okay. Is I like to split these things in half, and I like to think about what my cations are and what my anions are. So I know that I've got a barium 2 positive cation. I know that I've got 2 nitrate anions there. I'm going to do the same thing here. I know that I've got 2 potassium cations and I've got a sulfate anion. So that helps me understand how things are going to pair up. Because I know that a cation always has to get paired with what? An anion. It has to, so the charges cancel. So, like you guys told me, we're going to pair cations and anions. There's only one other way to do this. So barium now has to get paired with sulfate. And potassium now has to get paired with nitrate. Okay, any questions on how I was able to figure that out? All right, first I'm going to balance and then I'll worry about which one is the precipitate or not. So notice that I had 2 potassiums and 2 nitrates, so essentially that tells me that I just need to have a 2 here, and that's going to go ahead and balance my reaction. Thinking about the solubility rules, I sometimes think it's easier to think about which one of them has to be soluble, okay? And one of those is quite obviously the soluble product based on what we know about alkali metals and nitrate, right? Alkali metals are almost always soluble and nitrate is always soluble. So KNO3, that is going to be aqueous, which means that barium sulfate is going to be your solid. And you can double check that looking at the solubility rules for sulfates. Sulfates are usually soluble unless it has barium, so this is one of our exceptions, and that's going to make it a precipitate. So in order to do the spectator ions, you kind of have to do the net ionic, but I'm just going to do it real quick for you. Remember that when something is aqueous, that means that when you put it in solution, it's breaking apart into its ions, okay? So I know that barium sulfate is a solid, which means it can't break apart into any ions. It's like that picture we saw where they're all clustered together on the bottom. But the potassium nitrate can. So we still got 2 potassium ions and 2 nitrate ions there, all right? So your spectator ions are exactly what they sound like. They're ions that don't do anything. They stay exactly the same from the beginning of the reaction to the end of the reaction. So when you write out all of your ions broken apart like I did, all you're looking for is ions that are exactly the same when I started as when I ended. So I can see that I started with potassium as an ion, and it was still an ion in the product because it was involved in an aqueous solution both times. It was still floating around. I can say the same thing about nitrate. So potassium and nitrate, those would be my spectator ions. Okay, we don't really have another name for the other ones, but if I were to write the net ionic equation, all I would write in the net ionic equation are the things that are actually reacting. So all I'd write is Ba2 plus aqueous, reacting with SO42 minus aqueous, making BaSO4 solid. So that's all your net ionic equation would include, is just the things that are participating in the reaction. So before we work through these, there are a couple of things I want to say about oxidation numbers just so we're clear. An oxidation number is not the same thing as a charge. Sometimes a charge and an oxidation number end up having the same numerical value, but they are not the same thing. So when we write charges, you'll see it as something like 2 minus. When we do an oxidation number, you'd see it as -2, okay? I know it seems like a really stupid point, but they are different and they do signify slightly different things. Like I said, oftentimes they'll be the same, so the charge will be the same as the oxidation number, but they do mean slightly different things, and don't start getting confused when things that you are used to having negative charges have positive oxidation numbers. It doesn't mean you're doing something wrong, it's because oxidation numbers and charges are slightly different things. So let's go ahead and do our oxidation numbers. Like I said, I'd like to start with oxygen because it almost always has this -2 oxidation state. Do you remember when oxygen doesn't have a -2 oxidation state? When we should be aware of it changing? If it's in something called a peroxide, then sometimes it's not -2, but most of the time it's a -2. All right. What about the oxidation state of hydrogen? Do we always know the oxidation number for hydrogen? No, hydrogen can be +1 or -1, okay? So when we think about this OH group, okay, you should recognize the OH group as what? Hydroxide, okay? And what charge does hydroxide, the polyatomic ion, typically have? -1, okay? So if oxygen has this -2 oxidation state, whatever the oxidation state of hydrogen is, those need to add together to give me that negative charge. All right, so what does the oxidation number of hydrogen have to be in hydroxide? It's going to be +1, all right? So the oxygen is -2, the hydrogen is -1, all right? Now that means that each of these hydroxides has a negative charge. You'll notice that I have 4 of them, okay? But you should also notice that I have this little leftover negative here. So when we think about the oxidation numbers for things in charged compounds, we always need to be able to add the oxidation numbers together to get the overall charge on it. So I know that whatever chromium is, it is going to add to 4 groups of hydroxides, which is going to be -4, but it needs to add such that I have a leftover negative charge.
How come the hydrogen became a -1?
Sorry, it should have been positive. Thank you. Yeah. Definitely positive here. All right. So whatever chromium is has to add to those 4 groups of hydroxides to give me a leftover negative charge. So what can I add to -4 to still have -1? What kind of 3? +3. So in this case, chromium is going to have an oxidation state of +3, the oxygen is going to have an oxidation state of -2, and the hydrogen is going to have an oxidation state of +1. Thank you. Questions on how I'm doing that? All right, yep. Yeah.
So that meant the overall leftover negative charge is not having to do with the hydroxide, it has to do with like the...
It has to do with, it's the entire molecule. So that entire molecule still has a negative charge. Yeah, that's how to think about it. All right, let's look at B. It's kind of a similar idea. We have 2. We have got a sulfur that we have to figure out the oxidation state. We've got oxygen. We have to figure out the oxidation state. And we know that we have this leftover 2- charge. All right. We know that the oxygen is going to be -2. All right. You notice that we have 3 of them. So you can think about that as contributing a 6 negative charge. Whatever those sulfurs are, I need to multiply them by 2 and end up with a total of -2. All right, so 2 times whatever the oxidation number of sulfur is going to add to the -6 overall for the oxygens and give me this -2 for the molecule. All right, so as a group, what does the number have to be for those sulfurs? What plus -6 is going to be -2? Positive what? As a group, I know that that sulfur section has to be positive 4, right? 4, negative 6 is negative 2. You follow with that? So if as a group it has to be positive 4, that means that each sulfur is going to need to be what? Yep. Plus 2. Questions on how the logic of that works? What if it didn't have a charge? What if it was just neutral? Then what would I be trying to make the oxidation numbers add up to? 0, yeah. So it's a little easier if they don't have a charge. Okay, NO3 minus, again, we know that oxygen is going to be what? -2. I know that there are 3 of them, so that means I've got this -6 overall. What plus -6 is going to give me -1? Plus 5. Questions? As with most things, the more you practice it, the more sense it makes. The thing I want to point out, and the reason I'm saying that oxidation numbers are different than charges, notice that I just gave a positive oxidation state to a nonmetal. That is not saying it has a positive charge. Positive charges are typically reserved for what? Metals, okay? So you can have a positive oxidation number on a nonmetal. There's nothing wrong with that. The reason for that is that if you look at B and C, those are molecular compounds, right? There are no metals in there. So if the metal is not there to have the positive oxidation state, something has to. And that's why we're ending up with these nonmetals having positive oxidation states. That wasn't a problem for the first one because chromium's a metal and that's pretty straightforward. So just be aware that charges are not exactly the same as oxidation numbers, even though we kind of use both of them simultaneously.